Just talking about crack theory in the civil structures syllabus. Some of the textbooks refer to Griffiths theory, KIC. It's incredibly complicated university theory. I won't even try and simplify it. The textbook I had to learn was Tettleman and McEverly, and it was about that thick. Let's put it in simple English. Everything has cracks inside it anyway. The fact is that usually the cracks aren't big enough to worry things. You've only got to be concerned as a metallurgist when the cracks are big enough to influence the behaviour of the material. You've probably heard a teacher talk about stress raisers. That's essentially what we're looking at. So, in simple English, everything has cracks. I'm going to make a note up here. Optical fibres. Before I shut the video, if I don't talk about it, remind me to mention optical fibres and glass fibres. Okay, everything has cracks. Let's have a look at a metal with a crack. The stress, that crack is interfering with the cross-section that is holding up the crack. If that crack stops here, I'll colour it in a different colour, blue. That crack means that that's all the useful cross-section that's holding up the force now is left, yeah? So, if that's pulling there, that's pulling there, that means that force is basically bent around the tip of that crack. The sharper that bend, the higher the concentration of stress just in front of the bend. If I can get too much force in front of that crack tip, then it exceeds the yield strength and the crack grows. If, however, I've got a blunted crack tip or a rounded crack tip drawn at the same scale, the force does not get magnified over such a tiny area, which means in that area there, the stress is less and it might be below the yield strength, or more technically, it's probably not as high above the yield strength, so the crack does not grow so quickly. That is essentially crack theory, put simply. That's what you need to know for Year 12. Everything has cracks. You only need to worry about them if and when they affect things.